Okay, thank you very much. As I said, I'm Larry Kahn. This tech note number 4, determining the load capacity of a structure when as-built drawings are unavailable. And this is to convince you, don't give up if you don't have any drawings, right? We can still analyze structures and repair them, rehabilitate them, even without drawings. We'll tell you how. But first about Fred. Yes, this is Fred in real life. He's a good friend and has been just an outstanding ACI colleague over 40-something years, long time. He's one of the hardest working members as a TAC member. I was on TAC and TAC chair, and Fred did an enormous amount of work. He was chairman of the subcommittee for repair and rehabilitation. Besides being a chair of 364, as you heard, he was a subcommittee chair for the first edition of 562, the Concrete Repair Code, which was a challenge. He did a fantastic job, a long-term member of 546, and then was really successful in 563, repair specifications. Besides being a fellow here, as you heard, he's an honorary member of ASTM and fellow of other significant organizations. Winning the Delmar Bloom Distinguished Service Award is really impressive. Most of you don't know what it is, but if you do an outstanding job in service to a committee, you're awarded the Service Award, along with the Jean-Claude Romain Innovation Award in concrete. Some of you don't know, he really was a leader, a TAC chairman and all over at International Concrete Repair Institute. Fred has been a leader, but most important as a friend, he's a conqueror of the mountains around Breckenridge, Colorado, where we spent some summer sessions for technical activity committees, and while other people were gasping for air trying to do anything at 9,000 feet, he and I chopped on a Segway and ran all over the mountains in Breckenridge. You'll notice a sign behind Fred, yield to Segway. It's really yield to Fred because he was zooming around that mountain. So now getting to buildings where you don't have any plans. I show this picture. Yes, this building was built in the late 1920s in a coastal area in the South. Now, obviously, I had a hard time getting to it, going across the water, but in looking at this development and implementation of the first things you do is develop and implement some kind of investigation or an assessment program. And for that, you're looking at many things. I can't overemphasize history, just history of buildings in the area, visual inspections along with physical measurements, material testing, non-destructive evaluation. And yes, you can use a lot of NDT in investigating the buildings. That all results in an ability to do some kind of an analysis and calculations for which you can make some kind of determinations. If they don't turn out real good, well, maybe you can go to some load testing, which can actually save you a lot of money and give you some really good knowledge. You rely on knowledge, and I'll underline really experience and judgment to develop a cost-effective approach to assessment and rehabilitation. And this knowledge and experience are absolutely necessary. I'll repeat again later. If you don't have that knowledge, hire someone that does to help you to learn, because that judgment that comes from it is absolutely necessary for creative rehabilitation. In history, we really are interested in the age of the structure. That can give us a perspective on reinforcement materials. Certain materials were used in the 1910s, 20s, 30s. We changed a lot in the 30s and 40s. This had to do with concrete quality. It got better and better and better over time. It can also tell us things about the probable foundation types in many areas of the country. And you look at deterioration mechanisms, carbonization, that's really important for determining the pH of the existing concrete. If the pH gets down to around 9 or so, your reinforcement is going to corrode a lot, which Fred can tell you a lot about. But that means where's the inch and a half come from? A lot is at fire, but over about 50 years, that 1.5 will carbonate, your pH will reduce, and you can expect a lot of corrosion of reinforcement at that stage. So age becomes a really important idea. Well, how do you determine this? Well, you ask. You ask old people, really. You go to building officials and ask for the retired building officials and see, well, what was built down there? And I know working around Atlanta, that was great. I'm friends with some really ancient retired building officials. You say, well, what was built down there? Well, you know, when we had Gone with the Wind first performed in 1938, here's the way structures were in this part of town. So just ask, right? You're not expected to know everything. Ask people. In two codes, really in 562 code, you can find a lot of information developed from other things. First, looking over in your right, an outstanding publication by CRSI, Vintage Steel Reinforcement, and it gives you information on old ransom bars, even iron bars, structural steel dating from 1900. On the left, there's 562 gives you default compressive strength for structural concrete for various ages. So if your structure was built like in the first row up there between 1900 and 1919, and you have some kind of beams, you can expect a minimum strength of about 2,000 PSI. That's what they said to build it to. Because they use such large grain cements, then you have some active humidity in the air, you will get cores much, much stronger than 2,000 PSI. But you can go ahead and start analyzing the structure using these values. Visual inspection and physical measurement. The first thing you have to do is define what the structure is. Is it just a frame structure? Is it simply supported? Is it shear walls used for lateral load resistance? You have to define what that structural system is, which means you're going to measure slabs, beams, columns, walls, foundations, get dimensions. Yes, go out there with a tape measure and just start recording everything and use lots of pictures. You look at deterioration mechanisms. That is, you have large deflections. Typically, that's one thing an owner or a building owner will, when they hire you to have you come outside and say, well, there's a lot of cracking here, or there's a lot of deflections over there. You can use simple strings, simple levels. Just your eyeballs can tell you pretty good about whether you have excessive deflections. You'll see spalling, obviously. That's the bridges in downtown Atlanta. You have to wear a hard hat because the concrete will be falling on your head when you're inspecting. It's a lot of spalling. Rust staining on columns will show you a lot about reinforcement. And soft concrete, I'll talk about soft concrete in a second, because you carry around a hammer or a geologist pick like I do and just, listen, hammer and listen. Well, you're going to need to determine reinforcement size, position, D-distance, and layout for your calculations. One of the most important things is determine what kind of reinforcement you have for calculating moment and shear resistances. Non-destructive testing can help tremendously, but it requires validation. So you can do some tests, determine where some bars are, chip it off, find out what the real cover distance is in order to calibrate your tachometer, if that's what you're using, or ground penetrating radar. So tachometers are really good for shallow, right? 2 inches or so. You can get things down around 4 inches. More than that, it gets questionable. Ground penetrating radar, fantastic, except I have a tough time reading it, so I have to hire experts to actually read the results of what it's telling us. So this example is where there were a lot of cracks, actually, these are shown shear cracks here. You'll see there are shear cracks coming up over there. And it's like what was happening. We expected to see a lot of shear reinforcement. And so with the tachometer, we marked places where it was, where they were. We thought they should have been at like 3 inches on center. And so then we removed it to see actually what the depth of the cover was, and to check the tachometer was actually picking it up. The cover was only 1/2 inch, but that's what we determined. And sure enough, we knew why the shear crack was there. And in the beams, because there was about 20% of the shear reinforcement is we thought, the load would carry. But so you use the non-destructive techniques extensively. check it, verify it with physical measurements. Other times, it's pretty easy to see where the bars are. This is crawling around that building that I showed you on the coast. So we didn't need to map where the steel was. It was shown pretty close where the steel was. No concrete, but steel. You know, and it's rusty, but it's actually not too bad. And the concrete, except the stuff that had fallen off, was totally carbonated. Obviously, things rusting like mad down here. The advantage here is we also, in this crawl space, were able to see the top of the foundation, and we got down the sides and saw what kind of foundation system it was. Yes, you need the foundation system because in this case, we're in a fairly high seismic zone. The seismic loads were much larger than they ever were designed for. In fact, it wasn't almost designed for any seismic load. And so you need to know what's going on down there, right? Okay. Next then comes material testing, that is to determine. It's really common here at ACI to talk about concrete strength and taking cores. You know, if you're looking at flexural resistance, actually the concrete strength is not all that important. It's really where your steel is and how the steel is behaving. But it's good to know it. And so cores, there's a lot of information in ACI 214 about cores. It has all the statistics related with it in order to tell you how many cores you need to take in order to get a confidence limit or all that. Well, you can't take cores all over the place. So at least I have found that rebound hammer, probe penetration tests are really good for getting a general idea of uniformity of concrete around a structure that can limit the amount of cores you have to take in different places. In reinforcement strength, yes, you do have to sample. ASTM has some examples of taking bars out and actually testing them. But then after you have a few tests, in order to determine uniformity, you can certainly test for in-place hardness and particularly metallurgical filings. They can tell you, yes, you have the same steel or iron in one place as well as another place. So you don't need to be taking bars out from everywhere because they get expensive then to replace. Concrete quality, obviously petrographic analysis. So you take cores and some will go to the lab to see what's going on. And like I said, a lot of this is going to have reliability, things like confidence limit statistics. Well, ACI 214 is good for that. So is ACI 562. Even though you may not be using the code as a code, it is a tremendous, state-of-the-art document for telling you applied practice. Where I said about softness, we had trouble in Georgia with some ancient piles underneath the bridge. And the diver said the concrete's soft. And I said, what do you mean by soft? They said it's soft. So they at least took one out for me, brought it back to Georgia Tech. I had the grad students remove about 2 inches of barnacles on the outside. It was aromatic, to say the least, in our lab. So I didn't have to do it. That's why you have grad students. So we took it off. Here's the cores. Actually, about the outer 1.5 inches down to 2 inches, these little holes. We discovered a microscopic sponge that was eating limestone aggregate. The biologists were excited. We had a contact biologist say where the holes come from, but the sponges were well satisfied. But that changed the specification in Georgia and Florida. Well, in Georgia right away, no more limestone aggregate near the coast. Then looking in 562, again, you can find various tensile and yield properties of various ASTM over the years. So these, in effect, are going to give you some minimum yield strength that you can actually use in analysis. So looking again at the top layer, left-hand side, ASTM A15, if you have structures from 1911, 1966, a minimum yield strength for structural is about 33,000 PSI. Then there's intermediate hard. But if you don't know what you're doing with the structure, you're doing a first calculation, these kind of tables are great for saying, well, I can use 33,000 and let's see how the structure works. Before you need to be removing bars and all that, you just need to kind of see what's going on. For the foundations, at least in my experience, are the absolute hardest thing to look at. and some engineers don't look at it, but lateral loads have become one of the most important things to look at. High winds, tornadic activity here in the Southeast, and then as you go in some locations, some people like Pericles is real concerned with seismic. So you have increased vertical load, but really seismic and wind. You may need a geologic consultant determined foundation system. And I'd say not just may need, you really need a geotech. And the one thing they will do is talk about history of adjacent structures. And the only way to get around that is say, I'm ignorant, I need help. So again, who do you ask? Well, you can expose the foundation to determine deterioration and probable type. Even we structural engineers can kind of do that. And you can core, use a spectrometer, some NDT stuff, but really you need the geotechnical engineers to say, in this area of town, we more than likely had spread footings on certain kind of soils because in this area we have certain soils, right? Or they say, in this part of town, in Atlanta, right up at Peachtree Street, we have 30-foot piles that go down to granite, weathered granite. Okay, so you have a good idea of what you probably have under that structure from, again, old retired geotechnical engineers. And they love to talk, right? I mean, you have to get them some shrimp and grits or something for lunch, but they'll work for you. Okay. Sometimes you'll find original soil tests from adjacent structures. Sometimes somebody will have kept some kind of records. Not in the South so much, but in some localities like New York City, you have great records. Analysis calculation. Well, now that you've done all that work, you can take a shower, come back inside, and the span length, width, depth, D distances, and equivalent yield strength because of statistics, equivalent concrete strength, the connectivity of elements. You have loads from an original building code or from the current building code if it has to act, that is ASCE 7, as well as seismic from ASCE 41 if you're doing seismic retrofit. You analyze, you can use from 562 simplified methods. If you're just doing a beam, just analyze a beam. 2D analysis, you can go to 3D analysis. Some grad students in here, you'll go to nonlinear and finite element analysis. I generally have found doing that is more expensive than just coming down and doing a load test, right? I mean, you can start spending real money when you do advanced analysis, but sometimes that is absolutely the best thing to do in order to justify existing load levels or really understanding the capacity of the overall structure. Well, you get the load capacity, you say, does it work? And you need more data in order to do better statistics. A lot of times, if you've just done some simple stuff, simple statistics, use 33,000 PSI for your yield stress. You say, well, that's not enough. Let's go out and actually measure it. You find out it's 55,000. They use the really good grade of steel, and all of a sudden stuff works. So the owner will pay if you say, well, we need to go out and take some more tests. Load testing is often more cost effective, best for gravity loads. I think it's best for gravity loads and evaluation of flexural elements. 562 just says, go ahead and use the next one down, 437.2 code requirements for load testing of existing structures. There's a great report by ACI Committee 437, that's evaluation of structures. And again, if you're not familiar with running load tests, please hire an expert who is familiar with running a load test because safety is a major issue in load testing of structures. So you go out there and you load test. In the ancient days, well, really ancient days, they just tested with bags of cement. This is a very dangerous thing to do and also hard on your back. The other way is you puddle, you make a dam and you load with some water. That's nice unless it leaks and then the offices below and so forth get all wet and they're not happy. But jacking is generally a more modern technique where you have these little posts or have measuring techniques, but everything is shored So you see it being shored up to maybe an inch within the structure above. So if it starts deflecting more than you want, you catch it. Very, very safety oriented. And then you can run a couple of different techniques. That is a cyclic technique, which is allowed. It can get done very fast. Or the technique where you load it up to a level just really approaching yield stress, let it sit there overnight, and then you measure how much deflection has occurred, right? Both techniques are good. One you stay up all night with the structure, the other one you get done quick. So these are really good techniques, and I found building officials like results from load tests because, it's a load test. You actually loaded it. So with all that information, you now have evaluated load capacity of a structure without any drawings whatsoever. You have made your own drawings.